So, dear participants at various nodal centers and participants here in ETV studio, I welcome you again in this second session of our ICT program. And we are going to start with this session that is on logic optimization. So, after your RTL synthesis is done, means how you optimize the logic in your complete design. So, in this complete session, we are going to discuss. First of all, we will discuss overview of our design. Then, high-level synthesis we are going to discuss, and then logic synthesis. So, these two are major synthesis parts that normally we perform in our logic optimization. Based on these two syntheses, we get the optimized logic, and that logic is optimized in terms of resources, speed, power. So we are going to discuss how we optimize our complete design by using this HLS and logic synthesis. Finally, we are going to conclude our session and then references. So before going into the detail of our complete design, let us refresh you all about VLSI design flow also. This is one diagram from where you can easily view the design flow. Here you can see that our design entry, it can be in the form of VHDL or Verilog. So you have the option, you can go ahead with straight away schematic also, but here we have shown you the flow starting from VHDL or Verilog. So once your VHDL code is entered, you convert this VHDL code into its equivalent RTL with the help of RTL synthesis, and that RTL is nothing but it is a set of registers along with the complete information of netlist. Then we perform in this complete part, system partitioning is done. You partition the system, and this partitioning, system partitioning, will be done in HLS, high level synthesis. This is basically your synthesis part, and in logic synthesis and system partitioning, these two we are going to discuss in detail. How you partition your system, that will come under the category of HLS, high level synthesis, and then how you synthesize your design, that will come under the category of logic synthesis. And after this one, rest part is again your complete design flow. You have to floor plan, as we discussed in our previous session, how floor planning is done, and based on the floor planning you place your design, and then you finally route your design for hardware implementation. So this is complete overview of your complete design flow. Now your synthesis is basically used to assign resources to your design based on your timing requirements. And for example, if you want high speed, you have to assign more number of resources in order to get parallel design. If timing is not of major concern, then you can reduce the number of resources. You can go for serial kind of architectures. In that case, you can make your design cost effective, area effective, and but you have to compromise on speed. So depending upon the requirement, you can allocate the resources, and you can control the timing options in your design. And again, we can use pipeline registers. Pipeline registers are used to save already executed results, and those results can be used. Means you have those ready-made results in registers. Whenever those results are required for different sections in your design, you can use those results from the registers straight away. So we can say that these pipeline registers are also used to increase the speed of your design. So these registers can also be used along with your parallel architectures, or sometimes with serial architectures also. And as I told you, your complete design can be converted into major parts or two major logics. It can be data path logic, or it can be control logic. So first of all, you have to distinguish your design, whether your design is based on data path logic, or your design is based on control logic, or it is combination of both. So both can be there in your design. So now based on this, now we are going to start with our high level synthesis part. In high level synthesis, two major parts we perform here. First is scheduling. Scheduling is nothing but, you can say that, partitioning, scheduling your design, and second is binding or allocating the resources to your design. These two major parts you are going to perform in your HLS, high level synthesis. Scheduling means it assign operation to clock cycles, and different schedules may be possible, and a schedule which minimizes the cost, delay and area is the optimal one. So basically here you have to divide your circuit in different parts. You have to schedule it based on clock, right? And some parts need to be performed first, some parts need to be performed after the first one. So based on your requirement, you have to schedule your part based on clocks, and you have to take care of cost, delay and area. So your scheduling should be in this way. So once this scheduling is done, then you go for binding. Basically binding is nothing but you allocate the resources to your design. So as I told you, you can go for parallel design, you can go for serial design, depending upon your requirement or design constraints. Your design constraints can be area constraint. You have limited area, in that case you have to reduce the area consumption. Your design consideration or constraint, it may be your delay. You have to achieve results in at a very high speed. In that case you have a number of resources, you can those number of resources, and you have to take care of speed. So based on this, you have to find out one optimal solution. It doesn't mean that you have number of resources and you are going to use all the resources. Still you have to find optimal solution between your area consumption and speed. So based on this, now we are going to discuss how these two parts can be performed on your complete design. So actually you can divide your HLS in 5 major sections. You start with functional model programs. Means whatever program or Boolean expressions are there with you, you start with that. Then you divide them. As I told you, you can divide them in data flow logic and control flow logic. It is not possible to optimize your design for both the logics at the same time, right? So whenever data logic and control logic both are present in your design, you have to optimize them separately. So first of all, you have to distinguish data logic from control logic. Then you have to optimize data and control logic, and then again you have to stitch them together. So we are going to start with complete model program, different Boolean functions. You are going to separate out data flow. You are going to separate out control. Then you are going to stitching them together, data and control, and then you have to adopt some design methodology. So functional model is nothing but it is kind of you can say program that contains what? That contains your Boolean expressions. And Boolean data flow means you are based on 2 inputs, you are getting some output, and that output is used somewhere else. Control kind of logic is your, again, if else logic. If this is high, then make this on or make this off. So that will be your if and else statement kind of logic. And you have to make these two logics separately. As I told you, we have two kind of ASIPs, application specific processors. One is your microcontroller, another one is DSP. Because both these cannot be optimized together, that is why we have two different processors with us. Whenever you are dealing with control kind of applications, we always use microcontrollers. Whenever we are dealing with data flow kind of applications, we always use DSPs, right? So yes, if you want both, then you have to combine them, and you have to go for what? You have to go for ACIC kind of design. You have to develop your own ACIC. Just looking into that in our mind, we are going to divide data with from control. So let us say these expressions, you can say that these are the data flow graph where you are considering only data kind of expressions. It is free of you can say control statements, if else kind of statements. Here you can see that we are starting. This is the program where you have written this Boolean expression. It may be in your VHDL. Just like whenever you write your code of half adder, you write expression for sum. Sum is your A XOR B, and for carry, right? So likewise, these expressions are there in your VHDL code. We are extracting out these expressions, and now we have to convert it into data flow kind of graph. We call it as data flow graph, right? So here you can see that X implies A plus B, means A plus B, it is basically equal to your S X. Y is A multiply C, second expression. Third is Z. X is what? X is previously calculated X, that is used here now. X plus is added with some D, another input. Now we are using one more again X. Again we are using what? Y. It is previously calculated. Y minus D, and the last expression is your X, previously calculated X, just last X plus C. So let us say this is your Boolean expression that is present in your VHDL or Verilog code. Now how to proceed means how to you can say what we have to do now. We have to perform scheduling and binding, allocation of resources. How to perform that scheduling and binding part on these these 5 expressions. So first part basically is you have to convert these expressions into single assignment operators. Single assignment operators means you have to distinguish one variable from another. For example, X was at so many places, distinguish them. It was there at 2-3 places, but you can't distinguish which X. So you have to distinguish them, means now you are converting this Boolean expression into single assignment operator. So rewrite this equation, these Boolean expressions. Here you can see that X1 is equal to what? A plus B. Y is A multiply C. Z is, now we are using previously calculated X1. X1 plus D. X2 is, now X2 is what? Now we are separating it from X. X2 is previously calculated Y minus D. And X3 is now here. You can clearly see that we are using X2, not X1. X3 implies X2 plus C, right? This is the first step. So your VHDL code, from VHDL code you are going to extract the data expressions, data flow expressions. You have to convert those expressions into single assignment operator, right? So once it is done, then you have to create one DAG for this. DAG is direct acyclic graph. Direct acyclic graph means this graph is without feedback. You can see that you are starting with inputs and you are getting some output, and this graph DAG you have to create. First is your Boolean expressions. From Boolean expressions you are converting it into single assignment operator. From single assignment or operator, now we are creating DAG, direct acyclic graph, where there is no loop back, right? So just compare this DAG with those 5 expressions. What was your first expression? The first expression was X1 implies A plus B. So here you can see that this one A, B plus is what? X1. Output is your X1. Second one was, I think it was Y, and it was A multiply by C, and you are getting Y. Third one was your Z, X1 plus D, and fourth one was X2. X2 implies Y minus D, right? This one Y minus D, and the last one was X3, where X2 was added with C. So all 5 expressions are now complete here, right? So all those 5 expressions are now converted into DAG, direct acyclic graph. Now next next is now you have to schedule the operation. As I told you, major parts of your HLS, high level synthesis, are you have to schedule and you have to bind. First part is scheduling after DAG. Once DAG is done, you have to schedule. Schedule is nothing but you have to schedule different operations at different clock cycles. Means if first clock is coming to your system, which operation will be performed? It will be add, it will be multiply or subtract. That is your scheduling. So depending upon your requirement, you have to schedule based on your input clocks, means which operation will be performed first. So in order to perform this scheduling, you have to draw cut lines in your DAG, direct acyclic graph. These cut lines are nothing but your what we are basically going to partition. It is sort of partitioning. We are partitioning our design, means whole design is not going to be active at the same time. Some part of your design will be active at some time, and after some time some other part will be activated, and after some time some other will be activated. So based on this thing, you have to basically draw some cut line. For drawing this cut line, you have to follow some rules. It is not like that you can draw it blindly. You have to follow some rules, and you have to draw those cut lines. So now what we are considering here for drawing these cut line, we are considering for scheduling your operation. Here you can see that no more than one multiplication and one addition or subtraction can be performed per clock cycle. So basically you have to draw cut lines in such a manner that in one partitioning, means if first clock pulse is arriving, in one section you cannot perform more than one multiplication and one addition or subtraction. In this way, now you have to partition your design. You have to draw the cut lines, right? So this is the consideration that you have to take care in your mind. Now, based on this consideration, we have drawn the cut lines. In first one, you can say that we are performing addition and multiplication. In second one, we are performing subtraction and addition, and then last we left with only addition, so we are going to perform the addition. So you can see that you have divided your circuit in 3 different sections: cycle 1, cycle 2 and cycle 3. So these will be performed at different clock cycles, right? So this is your scheduling. You have considered some measurements before scheduling, means you are not going to perform more than 2 operations in one cycle. So we have drawn the cut lines for that. So I think it is clear to everyone. Now next step. So your scheduling part is done. You partition the design in 3 different sections. Now next thing is now binding. Binding is basically allocation of resources. Allocation of resources is linked with what? It is linked with area consumption. Whenever we optimize our design, we always consider area consumption, and your scheduling is basically linked with your speed, you can say, because you are scheduling your clock so that you can perform different sections of your part in a very efficient manner, so that you can get the output in very less time, right? So initially what we do basically, if you want to if you can see, when we partition our circuit, when we draw cut lines, some outputs are crossing those cut lines, right? It means that some data is data of cycle 1 will be used by cycle 2. So either you are going to give that data straight away to cycle 2. In that case, cycle 2 will have to wait for processing of cycle 1, or you can use what? Registers in between. For each intersection you can use register, and you can save data in those registers. So whenever cycle 2 means partition 2 need that data for processing, it can take that data from the register, right? So for that we can say that registers are used to store the data for each clock, and then you will get this kind of structure. For each crossing, you can say, at present we are not considering area optimization. We are providing or allocating one-to-one resources. Wherever whatever is required, we are providing. We are not considering any area, you can say, optimization. So here you can see that there were 4 crossings in cycle 1 and cycle 2. So we are using separate registers for all those crossings. Means each register is responsible for storing that particular number separately. We are not, you can say, this is non-sharing kind of resource allocation. If we can use one register to store 3 different results, that will be your what? Sharing kind of register. So at present we are not bothered about resources, just we are allocating one-to-one resources. Wherever whatever is required, we are allocating that thing. So cycle 1 to cycle 4, 4 registers are used. Cycle 2 to cycle 3, 2 registers are used, right? Next, but one-to-one binding wastes area, because not all values must be stored at the same time, and not all the values are required at the same time, right? So initially you have allocated resources, means your binding is one-to-one. Now you have to take care of resource allocation. We have to find out redundant resources. Redundant resources means those can be avoided if you can save some resources. So in that case, you can say that in this example, we can overwrite x1 register with x2 value, since both are not needed at the same time. You can say that x1, x2, they are not needed at the same time. So they can be, means one register can serve for both, right? Likewise, you can say that in one-to-one binding, we are using separate adders at 2 places, or at 3 places in fact, and all these adders are required at different cycles. They are not required simultaneously. If they are required simultaneously, means in just one cycle, then okay, we require 2 adders, but they are required at different cycles, so they can be avoided. Means one adder can serve for other 2 cycles also. So in this way, what will be your purpose? Actually, what is happening whenever you synthesize your code, right? Whenever your synthesis is performed, you will see in on your screen HLS will come. HLS is performed. So because it is happening at the back end of your design, you hardly you notice these things, because this thing is automatically done by the software itself. But you will notice that HLS is coming, HLS performed, right? So under HLS, basically you are performing what? You are performing this scheduling part and then your resource allocation part. So now from here you can see that one-to-one binding is done, and now you have to take care of area optimization. You have to remove the redundant resources, and then what is the option? How you can remove these resources? How we can use one adder in place of three? By use of multiplexers, right? We can use multiplexers, and then with the help of multiplexer we can use same resource for different cycles, right? So here you can see that mux, we have used mux, and we have reduced what? We have reduced adders from 3 to 2, and by using these multiplexers we have also reduced the required registers, right? This is your final data path, final you can say result of HLS, right? Two major things are there: scheduling, binding, and then in binding you have to remove the redundant resources, right? So once this HLS is done, then we move to control logic. Then one important reason to separate control from data is that just I told you, arithmetic rich and control rich machines must be optimized using very different techniques to get good results, right? That is why these two processors are different. Microcontroller is different and your DSP is different. So while optimization of arithmetic machines, we concentrate on what? Carry chain. Carry is coming, forwarding, you are controlling the carry. The optimization of control requires identifying the Boolean opportunities within the transitions. If else statement, you have to take care of if else statements, means what thing is changing when, and what to do if this thing is changing. So that is why we optimize them separately. So once your data and control is separately optimized, then what is next? Now you have to combine it. You have to combine it. Once we have completed an initial stage of data path and controller, then we need to plug them together and optimize the complete design. Now plug them and then further optimize it. And next is what? High level synthesis can produce useful productivity gains when used to automate the transform of architecture to transfer register transfer level. So whenever you change your design from HDL to RTL, it takes very important role. It plays very important role in that transition. So once your HLS is performed, in that case, your IBM HLS was one of the first industrial high level synthesis system, and it accepts what? VHDL. And actually what is happening behind your RTL synthesis? In RTL synthesis you are performing what? HLS, high level synthesis. So it accepts design description in VHDL or Verilog and produces register transfer level design, and this design can be input to IBM Bulldozer logic synthesis system. So once your HLS is there with you, now in HLS you have partitioned your design, you have allocated the resources, right? You have removed the redundant resources. Now it will be input to IBM Bulldozer logic synthesis. Now your logic synthesis part will be done here. right? So next part is your logic synthesis. So under logic optimization, two major parts are there: HLS and logic synthesis. HLS is already covered. Now we are going to perform this logic synthesis. Logic synthesis, basically it starts with what? Now what is in your hand? It take the logic description from your RTL synthesis. RTL synthesis is nothing but your HLS, whatever you have performed. Now it takes the RTL synthesis by stripping out the registers. Now whatever registers you allocated there, now you are again removing the registers. Again you are just using what? You are using just different gates and other logic. Now you are going to optimize that network of gates again. So after stripping out the registers, whatever registers you have used there, you optimize the network of gates that are required to implement that specific function. Again you optimize it. After your logic synthesis part, again you reunite the registers with optimized logic. So here we take that RTL description, we remove the registers, and then again we have a network of gates along with their network connectivity and netlist connections. And now we have to perform what? We have to perform logic synthesis. Now what is logic synthesis? As I told you, logic synthesis can be divided in two major parts. One is your technology independent, another is technology dependent. Technology independent, basically it works on you can say it works on Boolean your theorems, De Morgan theorem, different means whatever standard theorems are there, we use those theorems here for technology independent optimization. We use tabular method, K-map for logic optimization, because this optimization is not going to change from one vendor to another vendor. That is why we call it as technology independent optimization. It will remain same for every vendor, right? And whatever you perform in K-map, in Boolean expression, that part will be done under this optimization, that is your logic synthesis under technology independent optimization. Then your technology dependent optimization. Technology dependent optimization is basically it is based on different vendors. It varies from one vendor to another vendor. Because if you remember, in our complete design flow, in our implement design, we have three major sections. One is translation, translate, place, and route. Three things we perform, and that translate part is nothing but, so once you have optimized network of gates, means minimized network of gates, after what? After performing your K-map and applying your De Morgan theorems. So minimum resources, minimum you can say min terms, product terms, and some of product term is available with you. Now you have to, that is minimized network that is required to implement your design. Now for implementation of that network, you have to select some components available in the library. That also I explained yesterday. So each and every vendor have their own libraries. They provide number of options for one component. As I told you, let us say you are designing one half header. Half header is there in your design, and in library you have 20 options of half header, right? One vendor, they are providing 20 options, another vendor they are providing 15 options, another vendor they are providing 10 options. So it means that you have more flexibility where more options are there, and no doubt that software will be better as compared to other if you optimize the design. And that may be costly, but it may be of same cost, so you have to select that software accordingly. So that half header will be taken, and you are going to select one out of those 20 available in the library, right? Based on what? Based on cost calculation. You have to select the optimal you can say half adder out of 20, that is cost effective, area efficient, and if it can provide you good delay. So that thing is known as what? That thing is known as library binding, or sometimes we call it as mapping, sometimes we call it as translation, right? So once that optimized network is there, you have to map this network with existing components in the library. That is your library binding, mapping, and translation. So two separate optimizations are there. In first optimization, you have to perform K-map. You have to apply the theorems. In the second one, you have to select optimal components or optimal resources from the available in the library. So these two parts will be done. So here now you can see that you have library of vendor library here. We are what? This is the complete flow. HDL, RTL synthesis. RTL synthesis is what? It is your HLS. HLS, then we perform what? Logic synthesis. In logic synthesis, further you have two options: technology dependent and technology independent. And it is related with what? It is related with library, vendor's library. You have to use vendor library. So now from here you can see that library, logic synthesis, technology independent, technology dependent. Technology dependent can be your two-level logic options. Then multi-level logic means your K-map of with different number of variables, 4 variable, 3 variable, like this. And then technology dependent, you can see that it is totally dependent upon the vendor's library. It is going to vary from one vendor to another vendor, and because of this only your optimized results will be different. You may get better optimization if you have more number of options in the library, right? So now we are going to discuss first technology independent optimization. Right? In technology independent optimization, it depends upon Boolean simplification. Boolean simplification, it improves what? Sum of product terms. You try to make what? Pairs. If you can make group of larger variables, that it reduces what? It reduces number of product terms, right? If you can remove redundant covers, then it can remove your sum terms. So basically in our K-map or Boolean expression, what we try to do, we try to reduce the number of product terms and we try to reduce the number of sum terms. So that is your sum of product. So it improves the sum of product representation by taking optimal advantage of don't cares. You use don't cares and you try to make the groups, covers. So network restructuring, it creates new function nodes by finding what? New common factors. Sometimes you optimize or you minimize the expressions by taking what? Common factors, and you minimize your Boolean expressions. So all those basically standard minimization techniques or theorems or all those things you are going to apply here in technology independent optimization. So most commonly used method is your McCluskey, right? So this method is used to find what? Minimum prime, and minimum prime is related with what? It is related with your product terms, and redundant cover is related with your sum terms. So prime cover leads to minimum inputs to each product term, number of inputs to gate, right? And redundant cover leads to what? Minimum number of. So you have to work on both. You have to reduce the number of inputs to each gate and you have to reduce the number of sum terms. How you perform that? Let us say this is the Boolean expression: A bar, B bar, C bar plus AB bar, C bar plus AB bar, C plus ABC plus A bar, B bar, B, C. Sorry. So these are known as what? Min terms. First of all, we try to place these min terms, and you can say that this red color is showing these 5 min terms, right? You place it. Basically, whenever you use K-map, you try to make covers, but whenever you have to write it in algorithmic form, you have to find out some way how you can write the algorithm for that particular thing. So these 5 are placed. Then what is next? Next is, now you have to make the pairs, right? So here you can see that you have made 1, 2, 3, 4 pairs. If you can make the pairs, then we can reduce the number of what? Product terms. So first thing is, first of all, place all the functions, primes, and then make pairs of that. So after this one, now you have to remove the irredundant pair, which is not required. It means now you are going to reduce one sum term, right? So actually is this one. This is the table. You can say that min term versus prime table. And after this one, what we do? We reduce one redundant cover, right? So you have removed which one? This one. And we have used this. So in this way, now we have three sum terms, right? B bar C plus AB bar plus BC. AC is redundant, so you have removed it. So basically you perform this thing only in your K-map and Boolean expression. So in this way you can write algorithm for this one. So under whenever you are performing it at the back end of your PC, some algorithm is running, and this algorithm will be based on these different steps, right? So finally you get one structure that is optimal in terms of sum of product term. You have reduced the number of sum terms and you have reduced the number of product terms. Now you have one architecture. So that will remain same for all the vendors, as it is technology independent. Technology is not going to interfere in this one. Now once this minimized network is there with you, what is next? Your next step is, now you have to further optimize it. Now your software is going to play important role in this one. Now your technology is going to play important role in this optimization. So we are going to discuss one example how this technology dependent optimization can be performed on your complete design, right? So technology dependent optimization consists of your technology mapping. And technology mapping means it maps Boolean network to set of gates from technology libraries. Basically, whatever Boolean network you have now, it will be mapped with set of gates available in your library, software library, right? Each and every software, they have their own libraries, right? And they provide optimal components. As I told you, if you have to select half adder, they have different options, and each of option is optimal, but you have to select, still you have to select one which is more optimal as compared to others. Now when we start with our technology dependent optimization, what is there with you as input? Now input with you is technology independent optimized logic network. You have already performed what? You have already performed that technology independent optimization, and after that whatever network is received by you, that is there. You have to start from there. What next? Next is description of gates in the library with their cost, right? You have technology independent optimized network, and you have set of components present in the library along with their cost. Now, how to optimize depending upon your this network and library. Now, what is the expectation? What we are expecting from you, what you have to produce as an output, as researcher, as designer. You have to give us an output that will consist of netlist of gates from library, which minimizes what? Which minimizes the cost. Now you have to perform the mapping. You have to start with your network. You have to select the resource from the library. You have to calculate the cost, and you have to provide best solution. Means you have to provide a solution that is lower in cost. That will be your final output. Fine. Now we are taking one example here. You can see that. Let us say that is the circuit, or you can say optimized network of gates that you achieved from logic technology independent optimization. First one, and below is the components available in the library, right? This is the input, that network, optimized network, and different components present in the library of your software. Now there are different representations. Here you can see that different gates, what gates are used in your network, and what are the option in your library, right? So these are different gates. You have inverter, you have one 2 input NAND gate, you have 3 input NAND gate, 4 input NAND gate is also there. Then there is one Boolean expression, another Boolean expression. So these are some components, and you have some equivalent components in library, and you have to select from them. Now here you can see that 2 input inverter, it is represented by inverter only, right? Just one inverter is there. You don't have any option. You have to select that inverter. For 2 input NAND gate, that is required in your network. In the software library, you have one 2 input NAND gate. You don't have any other option. So straight away you have to, means here you don't have any option. You can't select any other. Just I'm going to give you this example from understanding point of view, but maybe in actual software there may be 10 options for 2 input NAND gate also. But here, in order to make this explanation simplified, so that you can understand the concept, what is running behind the software. So that is why we are just considering this. This is just consideration, but in software there may be components for 2 input NAND gate. Here just we are taking this as example. Next is what? Next is your 3 input NAND gate, right? Now 3 input NAND gate has one representation. It is like this, right? 4 input NAND gate, it can be represented. We have two options. Here you can see that it can be represented by this, or it can be represented by this. Then those two logics, it has this representation and this representation in the library of your software, right? So required resources and their equivalent resources available in the library. So you have these options. Now how to map, how to select. Along with this, here you can see that element or area cost is also mentioned. These numbers. For inverter, it is 2, right? For 2 input NAND gate, cost is 3. So as I told you, your optimization will depend upon cost. You have to select the resources in order to reduce the cost. So you should have that idea also, means what is the cost. So cost of 2 input NAND gate is what? It is 3. Cost of 3 input NAND gate, it is 4. Cost of 4 input NAND gate is 5. And Again, your first boolean network is cost is 4, and the other one it is cost is 5. So now with this information, we move further for our what? For our technology dependent optimization, right? So you have with you required number of resources, resources present in the library along with their cost. Now we are starting with our optimization part. Your first thing is you calculate the cost of each and every gate independently. Initial. Our initial start is we are calculating what? We are calculating cost of each and every gate independently. Here you can see that there are number of how many number of inverters? There are 5 inverters and there are 7 NAND gates. So as per our information, how many the cost of inverter was 2 and cost of 2 input NAND gate was 3, right? So you just calculated 5 inverter with cost 2, 5 multiplied by 2 is 10, then your 7 NAND gates cost is 3, 7 multiplied by 3 is your 21, and your total cost is 31, right? If we calculate cost of our network independently, we are not considering any other option at present, then cost is what? 31. Can we do better? No, there your optimization lies. Now your aim will be you have to reduce this cost from 31 to some value, right? So we have to move further. So what will be the procedure? We have to start from input and we will move towards the output. We will start calculating the cost of each and every component, right? So initially we are going to start from where? From input side, and we will move towards the output, and there our optimization lies. We are going to perform the optimization in that manner. Now first, your first gates, we are starting from left side and we have to move towards the right. Left, what we have one NAND gate, 2 inverters and another NAND gate. Cost of this one is NAND gate is 3, inverter 2. Just write down the cost of each and every gate. Then move to the next one. Now after this NAND gate, what will be the cost? Cost will be 8. Why 8? Yes, you can see that 3 plus 2 and 3 of itself 8 and here it is 2 because still we are not at that point, and here it is 3, inverter 2, and it is 5. So write down the cost at each and every point when we are moving from left to right. Then next, in next case, because up to this point there is no option, you can't choose anything. Then in this point, when we select another, so here you can see that at this point it is 13. 13 means 8 plus 2 of this one plus 3 of this one, and here we are getting what? 13. And at this point it is 3 plus 2, 5 up to here, and then what? 3 of this one. It will be equal to what? 8. And if we replace it with 3 input NAND gate, then cost will become 4. So we have one option. This same structure can be replaced with one 3 input NAND gate that is already available in the library, and that is going to reduce the cost to almost half. So here we are going to replace it with what? We are going to replace it with 3 input NAND gate, and you write down there as what? 4, like this, right? So we have selected one option that is more optimal as compared to the individual gate selection, you can say, right? Then next, in next one, up to here, what was the cost? It was 13, and if we calculate this, then it will become what? It will become here 15, right? But if we replace this architecture, this one, with this architecture, then this total will become what? 4 cost. It is 4, and then what is the subtree? It is 4 plus it is 3, it is 2. 4, 3, 2, it is what? 9. Otherwise it was 15. So we can replace this much portion with what? AO2 1, right? So we are writing there what? It is 9. 9 means complete. 4 of this one, and 3 plus 2. 3 plus 2 is 5, plus 4, 9, and below 1 it is 4, but it is already mapped. Then next, move to the next one. 9 plus NAND gate, 3, 12, and plus what? 4 or below. 9, 4, and 3, that is area cost is what? It is 16. Now I'm finding out some options. Let us say if we use this subtree up to here, right? This is 4, and we are using what? 3 subtrees. One is this one is 4, and by using these subtrees, subtree 1, subtree 2, subtree 3, and our total cost is coming, it is equal to what? Area cost of 18. But after using these 3 subtrees also, we are not able to get the minimum cost. Minimum cost is still with 16. So we will keep that 16, and we are not going to replace it with 18, right? Up to here it is 16. Now, the next option, again straight away use what? Use inverter. 16 plus this inverter is equal to what? 18. 16 plus 2 is what? 18. But again, if we use subtree, subtree is up to what? Up to here it is 13, and up to here it is 5, and this is equal to 4, this red one. So 13 plus 5 plus 4 is equal to what? 22. It is more than 18, right? So it is more than 18. So we have to keep what? We have to keep 18 as our area cost. Then write down 18 there. And next option is what? Next option is, if we take straight away 3 of NAND gate, then what will be the cost? 18 plus 3 is what? 21, right? If I use subtrees means this one 9 up to here, right? 4 of this one and 4 of this one. So it is 17. Earlier it was 21. In previous case, here This one. When we calculated it separately, then it was 21. And when we used 944. 944 is your 17. It is better as compared to 21. We will go for some other option also. Calculate 8 plus this 4 plus this. What is this? This 5 input and plus this 2. What is the total cost? It is 8 plus 2. It is 19, right? But still, which one is better? Our 17, right? So this is the same option. So what is your final design? Your final design will be of this one, 9, 4, 4. So you can see here. Now what is your final mapping of your network, optimized network? Your final mapping is for finally mapping your optimized design. What we need? We need AO1 to 1, 1 ND3, 2 ND3. You need 2 ND3. So these are required in your design. So in this way, you perform what you perform? Logic synthesis that will depend upon your logic, technology independent and technology dependent optimization, and you try to reduce the area cost of your complete design. And what was initially? It was 31. So it was 31. So you can see that from 31 you have reduced it to 17, almost half of that. So you can see that means even after your technology independent optimization, you have the option, you can reduce it further to almost half, right? So these are very important, you can say, parts where you can work. Now, as I told you, these are selected for your final what? After this logic synthesis, what is next? In design implementation, translate, then your place and route. Now, after logic synthesis, what is left with? We are left with placement and routing. Now, it is decided your this final design need one AO1 to 1 and 2 ND3 gates, right? It is decided. Now, next thing is what? Next thing is you have these gates. You have at number of places on your existing chip. If you are using PID, it may be your CPLD or it may be your FPGA. You have number of CLBs, and each and every CLB contains this logic. In case of ASIC design, again, it is present at number of places. So where to place it? So now, depending upon your IO inputs and output selection, you will define the IOs for your complete design. Depending upon that IO, first floor planning will be done. As I explained in our previous session, you will select the floor that is closer to the selected inputs and outputs in order to provide shortest path length, right? So that will be selected, and once it is selected, then you have selected one floor. On that complete floor, there may be 20, 30 CLBs. So you have to select one CLB out of those 20, 30 CLBs. Again, you are going to select that particular CLB which is closer to the IOs in order to provide what? In order to provide shortest possible length, right? So once that CLB is selected in case of FPGAs, and again in case of ASICs, once that particular area is selected, you place your circuit on that. And these three resources of your library will be used, and you are going to place your design over these three libraries. So once this floor planning and placement is done, finally you have netlist. and that netlist gives you complete information about connection between different gates or resources. So you freeze your design by final routing. You complete the design, you freeze the design by final routing, and that is your final design on FPGA, right? But in case of your ASIC design, what you get on your ASIC design, you get actual masks, right? In that case, here we are selecting CLBs with the help of floor planning. There also you may have different regions of transistors, right? So transistors are available, and by using those transistors, you have to select some particular areas. And transistors are available in the form of what? In the form of masks. You can say those are known as hard core IPs. Soft core IPs and hard core IPs. Soft core IPs are your those are your developed codes. You can straight away use those codes, and you can design your system. Hardcore IPs are your in the form of masks, right? Sometimes those masks are available outside. You can use those masks for design on your chip, and sometimes these transistors are already prefabricated on your silicon area, or there may be this NAND gate may be prefabricated on your silicon area. Why this thing is required? Because if you are using or you are designing your chip fully custom, right? If you want to create each and everything at your own, it is going to be time consuming. Time to market factor is very important factor. You have to take care of time to market factor also. So in order to reduce market time, what we do, we always provide some prefabricated resources on your silicon area, and those prefabricated resources may be transistors, those may be your NAND gates, those may be some modules of higher configuration, modules of higher configuration like your half adder, half subtractor, full adder. There may be multipliers also. So there is no need to create them again and again. You can use those IPs, hard IPs or soft IPs straight away, and you can use them in your design. For example, if you want to create any microprocessor, any microcontroller, DSP, and if you think you can start from transistor and you can go up to processor level, you can't, right? If you are dealing at processor level, you are designing some MIPS processor, ARM processor, number of processors are there. If you are going to design those processors, then you need some IP cores, right? Number of resources are required. You can use those resources, and you can use them those resources optimally by performing these logic synthesis and other parts, right? So in this way, we can design front end. In front end, you have to select CLBs and PLBs. In back end, again you have to select some prefabricated resources, and those prefabricated resources may be already there on your silicon area, but their mask can also be there. If that mask is there, then that is known as your hard IP core. You can use those masks, then you can create regions of those transistors or gates. You can use those masks, you can create those. In that case, okay, what is the advantage? If you have prefabricated transistors or NAND gates or other resources, what is the drawback? It is less time consuming, but again, drawback is your area utilization will be less efficient. Just like FPGAs. In FPGAs also, you may have 10,000 K of gates, but out of 10,000 K of gates, you are using only 100 gates. Like here, if you use prefabricated resources in on ASIC, it is there. It means that you are already using that much area of silicon. You can't reduce the size of your chip. Okay, so you have the limitation. You can't reduce the size, and your area utilization will be less efficient. Means you can use 10% of the already prefabricated area, and 90% of the area is not used. There your placement will not be efficient, it will not be optimal. Your interconnections you have to select from the already available, that will not be optimal. So advantage of using mask, it may be slightly time consuming as compared to this prefabricated, but in that case you are going to use only those masks which are required in your design. For example, you need only a NAND gate, 3 input NAND gate. So I am going to use mask of 3 input NAND gate on my silicon area. Wherever it is required, I will use that 3 input NAND gate, and I am going to use only that minimum area, right? So that is the advantage of those hard IP cores. Straight away you can use, and you implement only those resources which are required in your design. And another option is fully custom, you have to design your home. So different options are there, you can go ahead with your design. So you can work at different parts, and in this way you can optimize your design. So you can perform optimization at each and every step, starting from your HDL code to RTL. So you can see that we started from HDL code, we converted into RTL. Again, optimization is there. What is that optimization? That is your HLS. HLS is there. Then from RTL, again we are performing what? Logic synthesis, that is containing what? Your technology independent and technology dependent optimization. Then you are moving to what? You are moving to placement. In placement, again you have optimization. You can use different algorithms, min cut algorithm, thermal annealing algorithm is there. Even in floor planning you have the algorithm, how to select that particular floor in order to take care of what? Take care of shortest path. And after that you have what? After placement you have routing. There again you have algorithm. So those algorithms are your maze routing is very important algorithm. And one more algorithm is used, that is Disketra, that was used in computer networks. That is also for shortest path. That can also be used here in this. It is not like that it will be used in computer networks only. It is used to find out the shortest path, and here also we are finding the shortest path. You can use that algorithm also here. So once your routing is done, your design is now complete. Whether it is your front end design or it is back end design, now it is ready for use. You can use this design in your actual environment. So from here we can say that you can optimize your design in any one of these areas. So wherever you have interest or you are convenient, you can select any particular section and you can start work there. So you have different options. So with this we are now going to conclude. Design synthesis tools are used for RTL synthesis, that performs what? That performs HLS, high level synthesis. And then after this HLS we remove the registers again. Then we perform what? We perform technology independent optimization, and then we perform technology dependent optimization, and then again we allocate those registers, and finally we come up with one design, and that can be used in your actual environment. So with this I finish this session here, and these are some references for all of you. Again it is very good book, that is CMOS VLSI design by Neil Veste. Then another book is there, Modern VLSI design by Wayne Wolf, FPGA based system design by Wayne Wolf. Then user manuals by Xilinx ISC and lecture notes by Xilinx University Programs. And here I would like to inform all of you that it is always better to use user manuals of different softwares. They give you maximum information, and most of the books, they are also following those user manuals, right? So user manuals are best friends for you. No one is going to give you information about different softwares. You have to you need just our purpose is to give you initial start, or you can say spark, and after that you have to move ahead, and you have to get motivated in that direction, and you can work independently. Let me tell you, if you think someone is going to come there at your end, and they are going to explain each and everything to you. It is not like that. These type of STCs can give you initial start or spark. These type of STCs are to motivate you so that you can find out some you can say direction of research. And after that, if you are comfortable with that area, you have to explore those softwares. And each and every software is basically uh, provided with its user manual. Even your MATLAB, your Simulink, your these Cadence softwares, Xilinx softwares, every vendor, they provide their user manuals, and those user manuals are really user friendly. Download their PDF files, open them on your screen, open your software on your PCB, read that manual, perform those tasks on your PCB side by side. And I am telling you, one manual cannot take more than 1 month. Within 1 month, you can be expert in that particular software. And with these words, I just finish my session here. And now I